Hey everyone, welcome to another session of CeerazzleDazzlephysics. In today's session, we're talking about the photoelectric effect, guys. So put down today's title, it's going to be the photoelectric effect. Okay, and before we get going, guys, make sure you hit the like and subscribe button to keep my channel going, and subscribe and turn on all the notifications. Okay, so this is a A-level concept, guys, and it's quite tricky when we first start. And obviously, we've never done anything like this before, but we'll walk you through this entire concept. So we're going to start off with drawing the following. I'm going to draw over here a metal plate. Here we go. Here's a metal plate. There we go. Here's a metal plate. Underneath this metal plate at the top, we're going to connect another piece of metal. So another piece of metal is going to be coming out of the bottom over here. So imagine a plate on top and a piece of metal underneath it. Then, to this piece of metal, this bar over here, I'm going to attach on a little hinge. So imagine there's a little hinge right there, a hinge point, like a door, which is going to open. Here, at this hinge point over here, we're going to attach a thin piece of gold foil. So over here, this is a thin piece of gold foil over here. Okay, right, so we're setting the scene first of all, yeah, we're setting the scene. This whole experiment is called the gold leaf experiment. So this is called the gold leaf experiment. This is called the gold leaf experiment. Right, so we've got a plate on top, we've got a piece of metal underneath, and attached to that piece of metal there is a hinge point and a piece of gold foil here. Right now, due to gravity, this gold bit of foil over here will fall down. So it will actually end up being like this. So naturally, because of gravity, it would be against the other plane over here. There we go. So it'll be resting alongside it. But we're going to do the following right now. What happens if we are to add electrons to the top plate? If we were to maybe use static electricity, get some electrons and place them onto the top plate, what would happen to this gold foil? What would actually happen? Well, let's try and draw it out here. So we've got the metal plate at the top over here. And guys, obviously, this metal frame bit is over there. And now we're going to add the charges right now. So here we've added some electrons. There we go. They're going to travel down the metal pole and they're going to go along that gold leaf or the piece of gold foil over here. And obviously, well, if electrons go down it, then that piece of gold foil will be negatively charged and the metal plane will also be negatively charged. Those two will repel. So the gold leaf swings open right now. So if we charge it, the gold leaf swings open. So when charged, gold foil is repelled. Excellent. So the gold foil is now repelled over here. Right, so now we have this right now. We're going to do two things to it. We're going to shine visible light onto that top plate, and we're going to shine ultraviolet light onto that top plate. So what happens when we shine visible light onto that top plate? Let's draw it. Okay guys, so as you can see, the top plate is negatively charged, and as you can see, we've got that metal rod over here, which is also negatively charged, and the gold leaf is negatively charged, which causes it to be repelled away. When we shine visible light onto it, the observation is that nothing happens. Nothing happens at all. The gold leaf remains in its same position. It remains in that same position here. But something interesting happens when we shine ultraviolet light onto that top plate. So look, on this diagram over here, we're going to shine ultraviolet light. So I'm going to put it as UV onto here. And we notice that what happens? Well, look, the gold bit of foil over there has dropped down. So look, the observation now in this example, the observation is that the gold foil falls down. There we go, falls down. Excellent, so that is our observation. So when UV light is hitting it, the gold foil has fallen down over here. We are going to try and explain this entire experiment. So how on earth is this happening here? How is it possible that when I charge it and we shine invisible light, nothing happens, but when I shine ultraviolet light, the gold foil drops down. The gold foil is dropping down over here. The gold foil is dropping down. Right, now we can obviously explain why it's called the gold leaf experiment, because it's like a leaf in the autumn. Leaves fall down. That's the reason why it's falling down over here. That's the reason why it's called the gold leaf experiment. So ultraviolet hits the top plate and we notice that the gold foil has fallen down. There, the gold foil has fallen down. we are now going to explain what is going on here, what is going on in this scenario in a bit more detail. So let's discuss it with the following thing. Okay, right, so why did the gold foil fall down? Why did it actually fall down here? Right, so we clearly know that the only reason why that would fall down is because of the charge. So initially, obviously it was charged, but as it was falling down, there must have been less of a repulsion. So obviously it must be losing charge. So the key thing is that some of these charges were leaving the plate here. That's the reason why the gold foil was less repelled, and that's why it dropped down. So the only explanation is going to be that electrons were leaving the surface of the metal. So we're going to put that down right now. So therefore, electrons are leaving the surface of the metal. And as they are leaving the surface of the metal, they are taking charge with it. And there we go, guys. As electrons leave, they take negative charge with them. So as they leave, they take negative charge with them, and this leaves less charge on the actual bits over here. So obviously, as this becomes less charge, obviously as these electrons fly off, obviously there's less electrostatic repulsion, and therefore it falls down, because obviously there's less charge between them. Okay, so we have an idea that the UV light is coming in, and it is causing electrons to leave the metal plate. It's causing these electrons to leave the metal plate here. So now we're going to try and incorporate that all together here. So I like to explain this concept with the idea of energy going into the system and energy going out. So I'll start to write down the following here. Let's just talk about the energy here. The energy going in and the energy coming out. Right. So clearly, what's the energy going into the system here? It's coming from the UV light. So there'll be, on the left-hand side, the energy is coming from the UV light. So I've put EUV over here. Energy coming out. Well, you know this electron's going to be leaving. So as it leaves, obviously it's moving off. So as the electron is moving off, obviously it's going to have some kinetic energy with it. So we're going to put plus EK, E kinetic of electron. Yeah. So the ultraviolet light is coming in, it's giving some energy, and then some of it is being given off as kinetic energy of the electron. There is a term over here which we're going to discuss right now, and we're going to leave it blank right now, but I'm going to try and explain that right now. You're probably thinking, why did I leave a question mark over here? I'm going to explain it right now. So we're going to look at this diagram in a bit more depth. So we're going to look at this diagram in a bit more depth here. Let's have a zoomed in view of it. So let's say we've got our metal plate like this. There we go. There we go over here. There we go over here. So here's our metal plate. We've got the UV light coming into it right now. The UV light is coming in. And we know that obviously electrons are being liberated from the surface. So electrons, so E minus is going to stand for electron. Electrons are liberated. Electrons are liberated over here from the metal surface. Right, so let's draw actually what's inside the metal. So we should remember that inside the metal there are positive ions over here. Here are my positive ions. And I've got a sea of free electrons. So my electrons, E minus stands for electron, E minus stands for electron. I've got other electrons here. So I've got loads of electrons here. Right, as the ultraviolet light comes in, you know it's going to obviously help to release an electron. There's going to be a problem. So the problem is what? Look, if you're trying to liberate this electron, it's attracted to that positive ion here. So basically, you have got to give some energy to liberate the electron from its bound state, because you're going to have to rip it away from that attraction before it flings off. So that, guys, that energy is called the work function. Let's put that down. So the work function is simply this. The work function is going to be defined as, we've got the symbol phi over here. It's going to be equal to the energy required to liberate the electron from the bound state. There we go, guys. So the work function is equal to phi, and it is the energy required to liberate the electron from the bound state. You must liberate the electron from the bound state, and then the rest of it will be given off as kinetic energy. So I can now adapt this formula now and incorporate this term, the work function. So we can put phi over here. As you can see, guys, we said that the energy coming in is from the UV light. That will be equal to the work function, the energy required to liberate the electron from its attraction, and the rest of it will be given off as kinetic energy, guys. The rest of it will be given off as kinetic energy. So we're nearly there now. We're nearly there. We're getting a bit closer to actually explaining the photoelectric effect. We're now going to talk about this term over here, the energy from the UV light here. Right, now we're going to talk about the idea that light can behave like a particle. So all this time you've been talking about light behaving as a wave, but guys, now we're going to talk about light behaving as a particle, because this whole process will only work if the ultraviolet light has the properties of a particle. Right, so we're going to put that down. So light is basically a particle. There we go. Particle properties. So light, guys, can behave as a particle. So light can behave as a particle, guys. Right, so don't visualize waves going like this now. From now on, think of ultraviolet light or any type of light arriving like pellets or packets of energy. So ultraviolet light from now on, I'm going to redraw it as if it's arriving like a particle. So let's just draw it as like little paintball pellets over here. There we go. They're arriving over here. So they're arriving right now. The key thing is this. These packets of energy, guys, we're going to call them photons. So a photon is simply a discrete packet of energy. A discrete packet of energy. A discrete packet of energy. The word discrete means of a specific value, because the photon of visible light will not be the same as the photon for ultraviolet light, and that won't be the same as a photon for gamma radiation. So all of them will be different. So the photon is known as a discrete packet of energy, guys, and it is going to be related to the frequency of the wave. So a photon is a discrete packet of energy, and it's proportional to the frequency of the wave. Let's have a reminder of the electromagnetic spectrum. We know that we have radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, and gamma rays. We know that as we go across this spectrum right now, so as we go across this spectrum, we notice that we'll have a long wavelength at the start, and as you go across, it gets shorter and shorter. And then finally, as you go to gamma, it's even higher. It's even higher over here. So we can clearly see that as you go across this spectrum right now, the frequency is increasing. The frequency is increasing. So the frequency is increasing right now as you go across the spectrum right now. Right, what do you think is going to happen to the energy of the photon? What do you think is going to happen to the energy of a photon? It's something about the frequency. Well, the energy of the photon is proportional to the frequency. Therefore, the energy of a radio wave photon is not the same as the energy of a gamma wave photon. They're not the same thing. So we can relate them all together now. So we're going to put down the next statement. It's going to be the energy of a photon is proportional to the frequency of the light. Yeah, proportional to the frequency. Then, guys, we're going to relate it to a constant now. So E photon is therefore equal to a constant, and that constant is known as Planck's constant, h times by f, where h stands for Planck's constant. You'll be given this as well in the exam, guys, and that's a constant for all the waves, guys, for all the waves. And h numerical value is going to be 6.63 times by 10 to the minus 34 joule seconds over here. So the energy of a photon is equal to hf over here. Wonderful. So now look, now we've got this energy of a photon equal to hf. I can now add it to the equation we were looking at earlier on. So initially we said that the energy of the UV, well, that, guys, is going to be the energy of the photon. So let's just rewrite this down below. So we said initially that the energy is coming in will be equal to the energy coming out of the system. The energy comes in via the energy of a photon, and the energy coming out will be a combination of things. It is the work function phi plus the kinetic energy, E kinetic of electron liberated. Okay, right, so energy of a photon, guys, we can actually rewrite that, guys, to HF now. So we now can say HF is equal to phi plus E kinetic over here. E kinetic. And leading us to the following formula then, we remember that kinetic energy, EK, will also be equal to a half times by m times by velocity squared. So therefore, HF is equal to phi plus a half m v squared. I'm going to put an E subscript of the m because me is going to stand for the mass of the electron. Mass of the electron over here. Wonderful stuff. So look, guys, I'm going to just do that over here. There. Right. Wonderful stuff, guys. Right. This is known as Einstein's photoelectric equation. So this is Einstein's photoelectric equation. Photoelectric equation, guys. And obviously this whole process is called the photoelectric effect because you've shined photons, look at the word, and you've liberated electrons. That's the reason why it's called the photoelectric effect. It's really interesting because this will only happen if you can model light arriving as a particle. It will not work if you're trying to model it as a wave. Because if a wave is traveling inwards, obviously it will build up and liberate an electron. It's not the same now because for the photoelectric effect to occur, it's one photon for one electron to be emitted. Okay, so last of all, guys, we need the particle model of light as one photon liberates one electron. It's 1 to 1, guys. That's the key thing. It's like the particle model. Imagine like snooker. One comes in, it knocks out one of them. All right, and also if we were to visualize light coming in as a wave, guys, if a light was coming in as a wave, then eventually visible light could build up enough and then release one, which doesn't occur. So it doesn't matter how much visible light you actually shine on it, that could, it will never release an electron. You need to, obviously, that incoming energy of the photon simply must be greater than that work function. You need to, obviously, have more energy than the work function to liberate it. And don't forget, this work function is a constant for each material. So each material, its phi is also, it's a constant per material. Okay, so we have now done for another session, guys. In the next session, we're doing it in a bit more detail, guys. But for today, we've talked about Einstein's photoelectric equation, guys, and we've been able to explain it using the gold leaf experiment over here. Right, and obviously, if we don't charge the whole thing, the gold foil just flunks down, yeah? It's just down here. But if you were to charge it, it's moved outwards. It's moved outwards right now because it's being repelled. It has the same charge. The charge goes everywhere, and therefore it's repelled away. Then we shine a visible light onto it and we notice that nothing happens. Nothing happens over here. Then we shine ultraviolet light onto it and then we notice that the gold foil has gone down. The gold foil has gone down. But how can we explain it? So why did the gold foil go down? So now we're going to talk about why did the gold foil go down. We know that ultraviolet is coming in and it's liberating electrons and electrons are flying off over here. Electrons are flying off. And as they fly off, they are taking charge with them. Therefore, it becomes less repelled. Yeah, there's less repulsion, and therefore it falls down because there's less charge on the actual system now. So we then talked about energy coming in and energy coming out. We said that the energy comes in via the energy of a photon, and what's going to happen is some of the energy is given off as the kinetic energy of the electron. But then from there, we said that we have another thing that must be put into the equation. This is called phi. This is the symbol for the work function. And the work function is the energy required to liberate the electron from the bound state. You must liberate it because look, it's attracted to the positive ion. You must give some energy to break that attraction and the rest of it will be given off as kinetic. This is the excess kinetic energy from here. Okay. Then we said that, right, we have to talk about the energy coming in and then we talked about light behaving as a particle, guys. So light behaves as a particle. And we're going to say that light travels as photons, guys. So photons are basically a discrete packet of energy. Imagine them arriving like paintball pellets, guys. We can say that the energy of a photon is proportional to the frequency. So if I was to write down the electromagnetic spectrum, radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, gamma rays, we know that the frequency is increasing as you go across. So therefore, we can say that the energy of a radio wave photon is not the same as the energy of a gamma wave photon. So we can clearly see that the energy of the photon is proportional to the frequency. Relating it together, energy of the photon is equal to a constant times by the frequency. That constant is going to be equal to Planck's constant, which is 6.3 times by 10 to the minus 34 joule seconds. Okay, right. Then we said that we're going to take this energy of a photon equal to hf and put it back into our equation. So energy in is equal to energy out. Energy of the photon is equal to phi plus E kinetic of electron. Therefore, hf is equal to phi plus E kinetic. And therefore, we can replace kinetic energy with half mv squared. We end up with hf is equal to phi plus a half mev squared. This is known as Einstein's photoelectric equation, guys. And last of all, we talked about if we visualize light as a wave, visible light would build up and could cause a release of an electron. But obviously that doesn't happen. So the visible light, guys, over here will never release an electron. The reason why the ultraviolet one can is because obviously the energy of an ultraviolet photon is greater than the energy of a visible light photon. And then last of all, guys, we just talked about electron liberation is dependent on the incoming photon energy. That's the main thing, guys. And that's it for another session of Ceerazzledazzle Physics. Make sure you hit the like and subscribe button to keep my channel going, and I hope you enjoyed the lesson. Goodbye.